1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Still comes to 16. So you prefer sitting at the back than if you come in the front. You can interact much better if you're in the front. Instead of when you say something. I'll wait for another minute and then we'll start. Okay, I think we'll start. All right. So I think the first thing I want to say is that some of you all, or 1/3 of the class was of time. 9 of you are still not here, and a bulk of you are late. So I think in terms of students growing up, the first thing I've learned is punctuality. That is something which has to be part of your culture. From hundreds of applications, you have been chosen, okay, to give an opportunity across the country. And you're accountable for to come on time. It's not that your earlier class got late, your class got over on time. There's no excuse for not being on time. Okay. This is something which should be part of your upbringing in the country. Okay. Now, we'll get back to the subject of today's talk. Astrophysical jets, supermassive black holes. Now, waiting my colleague from IUCAA has already given you a couple of talks on active galactic nuclei, where he has introduced you. Okay. So first thing I'm going to ask you is, what do you understand by a jet based on what he has taught you? I don't want you to be deeper than that, but just depending on what he has taught you. There is this one. So was start. They come in. Let them sort that out. But anyway, start our discussions. So, what do you understand by it?
The matter that is thrown out of a black hole at relatively high speed.
That's a good start. Matter
Thrown away from a black hole for at relatively high speed that we observe with the eyes, we get to this matter.
Okay, you're getting warmer. Does anybody want to add to what she has said?
Due to strong magnetic fields generated by the
Magnetic field would be responsible for the collimation. Excellent. Anything else? Sorry. Bipolar. Okay. Collimated. Okay, that's a good word. Okay. So collimated outflow, and it did not necessarily have to be from a black hole, but that's fine because what he has talked to you about is active galactic nuclei, where the outflow is from a black hole. And you also mentioned about high speeds, but in terms of the wide spectrum of astrophysics, it need not be high speeds, very high speeds. So first what I'll try to do is the kind of jets which we see in astrophysics. Okay, and then we'll get into jets from supermassive black holes and the high velocities which is mentioned is अभी काम कर रहा है क्या? नहीं, हाँ? तो let me see काम आपका काम नहीं कर रहा है. Let's see. So what we will see in a short while when this gets sorted out is that jets occur in a wide variety of astrophysical situations. Now, what are the kinds of astrophysical situations where we can observe the jets? So we'll briefly discuss that, and then we will get into talking about jets in supermassive black holes, which are associated with active galactic nuclei. One of the early things. What happened?
You have to actually make that presentation in that.
Oh, okay. So, discuss about what you understand by the term, and we'll also talk about what are the different kinds of astrophysical objects for when jets are observed. The whole nitty-gritty of how actually jets are launched is actually still not very advanced. Okay, but we will look at a little bit about that. So let's look at the different situations under which astrophysical jets form. You've been taught about stars. Have you been taught a little bit about star formation?
Yes.
And star formation happens when a cold cloud collapses under gravity. Right? Now what happens is when a cloud collapses, there is angular momentum associated with the cloud. So because of the angular momentum associated with the cloud, when it collapses, velocities are going to get larger, and then along the axis of rotation, it's going to collapse and form a disk. Right? And that is called a protoplanetary disk. And this disk is the source from which the planets form. Right? From which the planets form. Planetesimals, small clouds coalesce together, attack more planetesimals, and then form planets. But when a star is forming, in addition to the protoplanetary disks, there is material with this high angular momentum which is carried away by bipolar jets. Okay. I was going to ask you when you said matter, what do you mean by matter? Because in active galactic nuclei, you have plasma which is relativistic. That means there are electrons moving at very high velocities and they are gyrating in a magnetic field that gives rise to synchrotron emission, right? Generally, high energies you could also get into stuff and we look at that. But when you talk about protoplanetary clouds, these are clouds, these are stars which are in the process of forming. So nuclear reactions themselves have not started. And what you have are cool clouds. If the cloud is hot, then stars will not form. Right? Why will it not form? Sorry? Particles have enough velocities, enough energies that it will counter a ground. So you need cold clouds, cold dense clouds. When we say cold dense clouds, they are the densest components in the interstellar medium, but they're still orders of magnitude less tenuous than the air in this room. But they're still the densest components of the interstellar medium called the giant molecular clouds where stars form. But when this protoplanetary disk is forming, then taking away the angular momentum, your bipolar jets which go out. These were catalogued initially by two astronomers called Herbig and Harrow, and they're called Herbig-Harrow objects, observation ones. This just gives you an illustration when initially the cloud is collapsing, it's initially thick because it's trying to make its way to this cloud that is embedded in. And as it progresses, you can see this cloud, this bipolar collimated outflow. Okay, outflows are breaking through, and these outflows are not because they could be just molecular cloud. Just you can trace it through molecular emission. You can trace it through carbon monoxide, which is transitions at millimeter wavelengths. You can look at water vapor, the water, which is molecular hydrogen, which is lines in the infrared. So, but these velocities are also not very large. You can see it's a few 200 kilometers per second. So it's rather slow, but it is still a collimated outflow, which we call it. But when we come to AGN, we see that they're almost moving out at a velocity of light, right? So this here, this is one which has been beautifully studied. HH stands for Herbig and Harrow. They were the two astronomers who first cataloged these classes of objects independently. And this is in the Orion constellation with a distance of 460 parsecs. And the protostar just embedded, you can't even see the star over here. That's where the star is from. So this is one category of bipolar rejection, where the material is not necessarily hot, it's cold, okay, relatively compared to the kind of jets that we talk about in the course of these lectures. And you can see, because of the line shades of nickel hydrogen in space and infrared, you can find out which one is blue shifted, which one is red shifted, so you can actually see the motion. You can actually see the shift in the spectral lines because of the motion. Okay. Often, when you take a large-scale continuum jets and radio frequencies, you can't see shift in spectral lines because it is continuum motion. Right? There's no spectral line. But in these kinds of objects, where there is a spectral line, you can actually measure the velocity from the shift in the spectral line. Other kind of bipolar flow which you see are called planetary. This is something which you have been introduced to in the course of lectures on the stars.
Yes.
Yeah. Okay. So this is one stage, the late stages of the evolution of a low mass star like our sun. It will go through the phase when it will shed its outer layers, and it appears as a fused kind of blob, and it got its name planetary nebula because it was large and it looked like a planet. So early astronomers, when they couldn't figure out what this object was like, they called it planetary. Obviously, they're not planets, right? Outer layers of stars. But what happens is, very often you'll see, a more or less circular kind of emission region. Sometimes that will be modified depending on the surrounding medium, because the material which is ejected is going to interact with the interstellar medium. But occasionally, sometimes these stars occur in binary systems, and the material which is flowing from one to the other forms a disk of material. And by interaction with the disks, the wind from one of the stars gives rise to bipolar emission. So these are also emissions which will satisfy the criteria which are outlined of bipolar, outflow, velocity, not necessarily large, and consisting of matter. Here, the material would be not cold like in the case of protostars, but it will be hotter. It's an ionized gas because the outer layers of the sun outer layers of the star are going to be hot and ionized. And you can see this particular one is velocity of 300 kilometers per second. So it could be slightly larger than the protostars. All right. So this is ionized gas, where you see bipolar. Then the exciting class of objects I have been introduced to it so far are the X-ray binaries. Have you been introduced to it? Yeah? Okay. So X-ray binaries occur in a binary system when mass from a companion star gets sucked in by a compact object. Okay? Because of the different masses, they evolve on different time scales, and from this disk, you can get jets of emission, which are moving out at velocity which is a fair fraction of the velocity of light. Some of these objects also exhibit what Vaidhi talked to you about superluminal motion. Okay? There are some of the jets who appear to move at superluminal velocities as well. Compact object could either be a neutron star. Basically, you need a very compact object to be able to get the maximum outer energy of the accreting material, or it could be a black hole. In this particular example, all the three objects are black holes over here, and these objects are also often referred to as microquasars. Why microquasars? Because the phenomenon of jets coming out at highly relativistic velocities is similar to what you see in quasars, but these are stellar objects. Okay? Stars in binary systems with a compact object accreting material from a companion star. Right? This will come to later. It's for a bit of detail on low mass and high mass binaries. Okay, what happens? The other aspect is you heard about pulsars, right? Okay, pulsars are very rapidly rotating neutron stars. Neutron stars are the remnants of the explosions of massive stars greater than about how many times the mass of our sun? Roughly about 8 times. Okay, if it is more than about 25 times, it will become a black hole. But roughly between about 8 and 25, slightly more dependent, that you get a neutron star at the center. And this neutron star, this is the Crab Nebula. Crab Nebula was discovered, went off in 1054 AD, or Common Era CE, and it was recorded by the Chinese. They say that historical records show that it was even visible during the daytime sky. It lasted for several months, and it left behind a very compact neutron star, which is pink. This particular object is called a Crab Nebula because the Ross looked at it first in 1844. It looked at the tentacles of a crab and called it a crab. Rotates about 30 times a second. Period is 23 milliseconds. You know what the fastest rotating pulsar is? Roughly? It's about
600 rotations per second.
It's about 1.3 milliseconds. If it were going to rotate much faster than that, actually centrifugal forces would just split it apart. Right? So about 1.3 milliseconds. And there's a whole category of pulsars called millisecond pulsars, which rotate with timescales of about milliseconds per second. Now, magnetic fields and all are going to correlate some of this ejection in the form of a jet. This is seen only at X-ray waves. You can see the bit more clearly over here. So, at least over here, the pulsar is so active that it fills up the entire remnant over here with high energy particles. And if you look at these images, radio, infrared, optical, ultraviolet, X-ray, you can see that if you compare the X-ray and the optical, X-ray is smaller in size. Then you compare the radio and the optical is smaller, X-ray is much smaller than the radio. Right? Do you know why that might be the case? Just guess. Very good. Can you have a little bit more? Okay, very good. But why? Temperature is low. Temperature is one aspect of it because you're very good, actually, excellent. So what is happening is that when the particles are generated inside close to the object, they're obviously traveling out, right? They're not going to just sit there quietly. So as they travel out, they lose energy. They're radiating away. So as they're radiating away, they're losing energy. And when they're losing energy, the lower energy electrons, lower energy particles will radiate at lower frequencies. So you see the radio one, which is larger. Radio is the lowest energy. In this red shown over here, but you can see that you can also see jets in the ground. The last one, I will sort of okay, are the gamma rays. Is that something you have been introduced to as well? No, not yet. Okay. So the gamma ray sky, these objects were accidentally discovered because the Americans set up this data set of satellites to actually monitor, when they had signed the nuclear treaty, to monitor possible nuclear explosions, which the Russians may be doing surreptitiously. Okay. But what they found was they recorded explosions, but they didn't seem to come from Russia. They seem to be from outer space. And today we know that these particles are these explosions occur can occur in very distant parts of the universe, and the amount of energy they release is enormous actually. Just for a few milliseconds, they can outshine everything else in the universe. The amount of energy released could be as high as about 10 to the power 54 Earths. So if you look at the luminosity of the sun, do you remember how much the luminosity of the sun is? Rough terms. Sorry?
10 to the power 30.
10 to the power 33 Earths per second. So, okay, excellent. So if you add up 23 ergs per second and multiply it by 10 to the power of 7 seconds in a year, and then you put in 10 to the power of 10, and 10 billion years is the lifetime of the sun, these gamma ray bursts emit more energy, some of them, than our sun will do in its entire lifetime. So they're among the most energetic events known in the universe. And although we do not have the resolution to map the jet, one way to understand the energetics of what is happening is that jets are created which come towards us at highly relative velocities, so that Doppler effects enhance the fluxes that we begin to see. So these are the kinds of objects besides the AGN, where in astrophysics you see jets of from the cold molecular jets in protostars to the highly energetic jets in relativistic plasma, in gamma ray bursts and active nuclei. So now we come to with this introduction to the wide spectrum of jets which you get in astrophysics. Let's zoom in on today and tomorrow on jets in active galactic nuclei. Now, Wendy has already talked to you about active galactic nuclei, so you have to tell me what are the observed characteristics of an active galactic nucleus.
They shine a lot. The luminosity from the center of such is
Excellent.
outshined everything.
Can outshine it. Can outshine it. Okay, so we'll write down it. She has said that it has a very high luminosity. The luminosity from the high luminosity, I just put it as high luminosity and can outshine the galaxy. Okay, outshine the galaxy. Right? High luminosity, one aspect. So what are the other things which you remember?
We can get spectrum in the range of all electromagnetic waves.
Okay. Okay, who said that?
From radio
Okay, very
to
good.
radio to
So you can see, okay, very good. Okay. So you can see that I just write down spectral energy distribution goes to the highest energies, right? Highest frequencies, let's say gamma rays. Okay, highest frequencies of energies. Excellent. What else?
they show strong action line.
Sorry?
They show strong action line.
Strong emission lines, excellent. Because when you look at the optical part of the spectrum of a normal galaxy, what you see are absorption lines, right? And where do you see absorption lines? Not presence of coal gas. Coal gas is there, but there's something more fundamental than that. Why absorption? Let me just write down emission lines. Okay, emission lines. Very good. Emission lines. So prominent emission lines. Okay. Okay. Very good. But I'll tell you the question that why do I see absorption lines in a normal galaxy?
In normal galaxy, the interstellar medium are much more filled with gases, which absorbs.
I mean, even if I took an elliptical galaxy, which doesn't have too much of gas, I will still see an absorption spectrum unless there is something, unless it's an AGN. Spiral galaxies have more gas. Gas can contribute, but that is not the primary reason. Yes. So when you look at the spectrum of a normal galaxy, what is the most dominant source of light in the normal galaxy? Stars. And what does the spectrum of the star look like? Absorption. So in a normal galaxy, what you're characterizing it is the addition of the spectra of all the stars. Right? There will be some rotation, there will be some publishers, but it's largely the aggregate or some of the spectra of all the stars. There will be contributions from the gas. There can be, and it varies from galaxy to galaxy, but a dominant contribution is from the stars because that's where you're seeing all the light, most of the light. Right? Okay. Now, anything else you want to say? High luminosity, spectral energy, highest frequencies, emission lines which can be very broad, from hundreds to thousands of kilometers per second, right? Moving around. What else? Jets, very good, excellent. Okay. Very good. Jets. So you've got almost all of it. Okay. But The other thing which we may not have mentioned about is that a lot of these objects exhibit. If you take a normal galaxy, it's sort of pretty constant. That's short time scales. So these are sort of defining characteristics of an active galactic nucleus, right? Active galactic nucleus, but not every galaxy not every AGN will exhibit all these characteristics. So you may see a subset of. So different kinds of active galaxies can exhibit different subsets of these kinds of activities which are exhibit. Okay, very good. Now we will also look at what kinds of AGN that you can remember and what are they. Now, before I do that, I'll keep it by the time. So when we finish, I think 3:30 we finish, right? And then we take a break for tea, right? And 4 o'clock we meet.
Yes.
So I'll keep it by the time. Okay. So this is just a little bit of history over here. We're coming to kinds of short while, where a collimated structure, but we didn't call it a jet at all because jets were not talked about at that point of time. Right in 1819, Curtis was looking at this famous galaxy called M87. You know what M stands for over here?
Messier.
Messier. You know what the Messier catalog is all about? Very good. Okay. You mentioned about a curious straight ray lies in the gap in the velocity, aptly connected nucleus with thin line. The way Michael just described. But those are the days when we didn't know of AGN, we didn't know of jets at all. Then Barton and Minkowski, many years later, 1908 to 1954, you can see how long it takes. They noticed several condensations in the outer parts, and they measured a velocity, and they said that the O2 line is shifted, and it's coming towards us, and the velocity is negative, and the jet was probably formed by ejection of the nucleus, but we had no information on either jet formation, longitudinal physical state. The whole field of AGN opened up at that point in time. But they were amongst the early ones to use the word jet. Early ones to use it. So what are the different kinds of AGN? So this is just to tell you about the jet in AGN as well as we talk about the kinds of jets. So what are the kinds of galaxies, different kinds of active galactic nuclei that our friend Vaidei talked Sorry, go ahead. Okay, very good. Right, very good. We come to radio galaxies. Lasers, okay, lasers. I'll write it down what you're saying right now. What else? Lasers, okay. Lasers. Actually, the zoo of galaxies is wide because people have classified the different. But there's one more very important type which must have mentioned. Sorry? C4 galaxies. Very good. Okay. So we will just quickly revise that, and the first class will just C4 galaxies. Okay. So we'll just quickly go through that, right? And then we will look at after 4 o'clock we look at it. Okay. So you know all about C4 galaxies. What is important about C4 galaxies is that a host galaxy is generally a spine. Right? So we'll just summarize these properties in here. So host galaxy is spine. Okay. And these were discovered by Carl Seifert by doing a spectroscopic survey of spiral galaxies. We found about 10% of them have a semi-stellar nucleus. So your point about high luminosity coming up from the center. But Seifert's, the nucleus is not that strong. If you took a very short exposure photograph, you'll pick up the nucleus more clearly. But you can see over here, this is the nucleus, but you can see the galaxy quite clearly as well. Whereas in some kinds of AGN, we see it can completely outshine it, as you have correctly mentioned. Okay, and this is the spectrum for normal galaxy we just talked about. This is the kind of Seifert one galaxy, and talking about the two types of sequence as well, right? Mm-hmm. So we talk about Seifert 1 and Seifert 2, right? So what do Seifert 1s have? They have Gauss lines, right? So what does a What does the presence of broad lines denote?
Emission.
What about the location of the line emitting region? Sorry. Closer to the black hole. Very good. Excellent. Because the gravitational influence is more. So just by applying Kepler's laws, you will realize that they are moving around at high velocities. So the broad lines are closer to this. And then you have, so these are the ones where you see broad lines plus narrow lines. The Seifert 1 and the Seifert 2, you see only the narrow lines. Right? That you remember. Okay, very good. So these are the two kinds of Seifert. This is just another illustration of it to tell you what they are. But for both of them, the most galaxy is narrow in terms of lines. So these are broad plus narrow. These are not quite narrow. I'll go through this rather rapidly because you're not quite familiar with it, but just realize. Okay. Now, Seifert galaxies also have jets. This is one such example, but this is the nucleus of the Seifert galaxy. It lies within that. We're not clear whether there's a nucleus or there's a component more compact with it. This is, don't worry about 1.5 and all that. From the spectrum, they classify it in intermediate types as well, but we're not worried about that. But you can see that there is bipolar projection along a particular axis, right? Now, in Seifert galaxy, this axis doesn't have anything to do with the axis of the galaxy. It can be a different axis, but when you see cones of ionized emission, it seems to be quite closely related to the cones of ionized emission. We'll look at one or two pictures of it in a short while. Okay? Now, I'm asking you questions, but if you have any questions also, please interrupt. No issue at all. Now, you can see over here that this is a Seifert galaxy. Now, jets are present, but what happens is that if you look at the radial luminosity, jets can be seen. Jets. But if I look at what I call radial loudness, these objects are, although we can map it in, if I take the ratio, if I look at the luminosities of this object, there will be about 1 to 2 orders of magnitude, at least less luminous than the radio galaxies. If I take a ratio of the radio flux density to say optical flux density, then you would have small values. So, although we use the term radio quiet, they're not exactly radio quiet, but they're radio weak. They're not like the radio galaxies that we talk about in short. So these Seifert galaxies belong to the category of what we call radio quiet objects. This is also radio quiet with Seifert 1. Now, radio galaxies are associated with radio galaxies, and you know how they were discovered. Just a little bit of history, good to know. Does anybody know how they were discovered? See, when radio astronomy started out, the first thing astronomers did was to make an image of the sky, did the surveys of the sky. Then they found these blobs of radio emission, sources of radio emission. The earlier work was done in Cambridge and in Australia. Then it was followed by other countries as well. And India is also one of the leading players in terms of radio astronomy. You all have been to the GMRD already, right? Okay. And tomorrow, Yash will talk to you about the square kilometer relay participation in it. And so when we found these sources of radio emission, which were basically sources of continuum emission, they were all over the sky, and they couldn't actually figure out what they were. So one natural thing to do was to see if they were optical counterparts of the sources. But the radio window was the first major window to be opened up outside the optical region of the spectrum. So then, let's see if it's associated with any kind of object. When they did that, then they found that for a nearby object, they could be quite certain. Because in the early days, the resolution was also very poor. Lambda by D was extremely poor. So when the resolution is poor, that means your seeing in optical or the beam in radio is very large. So what happens if the beam is very large? There's so many optical galaxies sitting over there that you can't see even which one is associated. But when you look at a nearby galaxy, the resolution is poor, so it looks like a large source. And your optical galaxy is also large because it's nearby. So if they bang on top of each other, you can hold your heart in your hand and say, oh, I think it's real. They're probably associated. So that's the way they initially identified the nearby luminous radio galaxies or strong fluxlets heat with relatively nearby galaxies. So these were Centaurus A, Virgo A, Onyx A, Hercules A, Cygnus A. All these are names of constellations. And A means it's the strongest source of radio, strongest radio source of radio. So later, when, of course, this was earlier, this is a very recent map, relatively recent map, and when we mapped this at higher resolution, we found that there was a nucleus and the huge knobs of radio emission, and there are jets connecting the lobes of emission to the central energy. That means energy is generated in the nucleus and it can be transported over large distances from the center. So we look at a bit how the energy is generated in a short while. But okay, so what we have is over here radio galaxies. Radio galaxies, the hosts are generating radio galaxies. And lines are usually narrow, too broad. And they're referred to as broadline galaxies. But the bulk of them are. So jets are often seen, and these are not radio line, but radio line. They're very luminous in the radio. And there are a few exceptions of spiral galaxies being associated with it, but it's literally numbers is something which you can calculate. So, of thousands and thousands of radio galaxies which have been catalogued, about half a dozen or so are associated with spiral galaxies. So, generally, it's okay to say that they are associated with elliptical galaxies. Now, we talked about these are more images of it, and radio galaxies. He also introduced you to the two classes, right? Panera Riley class 1 and Panera Riley class 2, right? Okay. So, can you tell me what Panera Riley class 1 is?
The magnitude of FR1s are
the luminosity. Very good.
the absolute magnitude.
Absolute. I mean, let's talk about the radio luminosity. Okay, it's lower than that. Okay, very good. Luminosity is one aspect of it. The other thing is that you can see a clear structural difference over there, right? There are low luminosity generally, but today we are finding the boundaries not as sharp from more recent surveys as it used to be. But you can see what the pointer. So this is the pointer. You can see over here that they do prominent edges over here, right? They do prominent. They just seem to expand out into diffuse fluids of emission. This is FR1, lower luminosity, and this one ends in bright hot spots. Here on large scale, jets are symmetric. On small scale, on large scale, jets are very one-sided or asymmetric. Right? I want you to remember this because we'll come back to it later when one of you mentioned very early on that geometry plays an important role in the way galaxies are, right? Quasars or radio galaxies. So I want you to remember this, right? So what does FR1 mean? I'll just write it over here. Because prominent hotspots at longer edges and more asymmetric. FR2 is those. And symmetric large edges. The reason why I'm saying large over here is because when you observe these sources also, the FR1 with very high angular resolution at a nucleus region, small scale you will find this. Okay, just remember that. And generally, although there are, this is also lower. Statistically, that's correct. Although that's changing a little bit. So, Panera, when you talk about astronomy in South Africa, which Vishwan hopefully will talk about tomorrow, Bernie Vanderhoff is one of the leading lives over there who got South Africa, the square kilometer away to South Africa. In fact, he's a very sort of versatile person. He did his PhD in Cambridge. He came back to South Africa. He was one of the leading fighters for labor rights. Was president of the miners' union. He did a variety of, and in South Africa's planning in the post-apartheid period, he played a role. And so, student Cambridge and supervisor was Julia Riley. That's how Vanderhoff and Riley. They wrote a small 4-page paper, and that name is stuck on classification based on structure. So this is just important. Just remember this, because we'll come back to it later. Right now, okay, radio galaxies and quasars. Just to illustrate to you some aspects of how large can they be. They can be very small because they are clearly going out from the nucleus, right? So you can be very small if you catch them down. They can be parsec scale or 2 parsecs, 1 parsec 3.26 light years. 1 light years is like per year. Yeah. And the largest ones are right now in the ballpark of 5 megaparsecs. That means 5 million parsecs. So you could get hundreds of Milky Ways lined up together, and you will make one of these large sources. These are the images made with the giant telescope. This was still recently the largest, but this is one particular image. It's also giant galaxy, about 2 megaparsecs, about 16 Milky Ways across. And this one is just illustrating that the jets may actually be there for some time, shut off, start again, and that is also something which we try to talk about not today but tomorrow, right?
So, rejuvenated radio galaxy means a galaxy whose jet has started again.
Has started, yeah. So you have the jet which has been, lasted for maybe 10 to the power 7, 8 years. For some reason, it just started off, and then it restarts. Now, this is the galaxy M87, but we meet M87 again and again here as well. I think one thing which I wanted to mention here is that, you see, this is the M87 galaxy which we talked about earlier, and these are all radio images, right? And you can see that they are talking about structures on different scales. This image actually talks about just this jet over here, this object, just a nucleus over here, and of course, this is the famous Event Horizon Telescope, image of the black hole. Now, when you make radio images, the image which you get depends on the location of your antennas. That is what I wanted to actually mention, because we keep looking at radio images. Because what happens is that, you remember what is the expression for angular resolution? What is it? Lambda by G, right? Now, normally, if you take a single telescope or even the human eye, D is the size of the aperture. Right? For example, if you take a few millimeters for your cornea and take nanometers or 500 nanometers for the wavelength of light, you'll get a resolution roughly in the ballpark of an arc minute or so. Okay? Now, when you have radio interferometers, which Neeraj will talk to you about interferometry. Yeah. Then the resolution depends on the location of the antennas, where D is not the size of the single aperture or single antenna, but the separation between the antennas. And when the antennas are very far apart, just one pair of antennas, then you will pick up the smaller scale structures. And you actually literally blind to the large scale structure. So the thing is that when you want to get a complete picture of a radio source, you literally got to combine data from all kinds of pairs or all kinds of separations. That is why you have GMRT, for example, see the antenna located in spacings, is to try and make up for all the different kinds of information which you sample with the different baselines. So here what you have is where you have small separations as well, so that you pick up a large scale structure. Here less so, here still less so. Only pick up the nucleus, you're completely blind to this large scale emission because you don't have close antenna data in your data. And when you look at the Event Horizon Telescope, you don't see anything else at all, just a black hole. Because the spacings are so large, you get completely blind to the large scale structure. You need antennas close by to get the large scale structure, and far apart to see the small scale structure. All right. You've done later, maybe at undergraduate level, you may not have done Fourier transforms, but this is related to the Fourier transform relation between the brightness temperature, brightness distribution of the source and what you're sampling would be atmosphere. This is just showing you energy 7 different energies. At radio frequencies, you see the jet. At very low, as we saw, this is a large scale structure. But when you go to the gamma ray energies, you will see it's going to take only the nucleus. This is just a revise. That C41, C42 you're familiar with now. Galaxies, radio galaxies normally have narrow lines, but occasionally a small fraction you will see also broad lines. So that is what we have. A normal galaxy is dominated by the absorption lines. Okay. So that's nothing wrong. Next you mentioned is quasars. Do you know how quasars were discovered? It's good to know a little bit of history, to make just the subject a bit more interesting. Does anybody know how quasars were discovered? No? So this was again trying to find out optical counterparts of radio sources. They saw this detected this radio source C273. Because the resolutions are poor, they couldn't identify just from the cataloging the source what the resolution is. But there seemed to be a star-like object, which was very unusual, right? Because other objects were associated with galaxies. But they needed a much more accurate position to be able to identify or find out what is the optical object that is associated with it. All right? What did they do? They thought of a clever thing. You see, the part of the moon is known very accurately. Known for a long time, the moon's path, catalogued by the US Navy as well. So this source was getting occulted by the moon. Now, if you know the position of the moon very accurately, right, and you know where it's getting occulted, you can determine the position of the radio source as well. And not only that, you have studied about diffraction. The moon's edge acts as a straight edge diffraction pattern. So if it's a point source, you'll get a very sharp fringes. If it's a very extended source, you'll get washed out. So you can actually infer back what the structure of the source might be by looking at the diffraction pattern of the ground, the moon as a. And obviously you can't tell the moon to go there, you go here. So it's getting occulted means you have to record the data and make sure you do your experiment here. So this was done in parts by Cyril Hazard, the team led by Cyril Hazard, and then they could determine the position very accurately. They took great precautions, they quickly located the data, recorded the data, duplicated two tapes, carried it into the two planes so that they weren't crashed, they still had the data, and they could determine the position very accurately. When they determined the position very accurately, then they knew that it was associated with the star-like object. Now, you all know by now that stars have absorption lines. Okay? So when they took a spectrum of the object, they found no absorption lines, but very prominent emission lines. Okay? Now, it was a puzzle for some time. So what these emission lines denote? And it was definitely genuinely an insight of Martin Schmidt to realize that they were nothing but the redshifted Barber lines, H alpha, H beta, H gamma, H theta. And at that time, we were only exploring the nearby universe. The fact that an object could exist when what we today know is a very modest distance was a very large distance at that time. So you had a star-like object, and this goes back to the statement you all made, can outshine the galaxy. So this is an object, a quasar, which is the nucleus of a very bright galaxy, and luminosity is so large that with existing dynamic range, you could not pick up the galaxy around it. And it's a very strong radio source with a one-sided jet. So this jet is also visible in the optical region of the spectrum. I mean, this was written by Martin Schmidt a long time ago, but today we have much better images, not only in the radio, but also optical, the Hubble Space Telescope, the X-rays, and they all overlap, but there are subtle differences between the jets as well, which if there is time we'll get into it, but is related to the different kinds of emission processes which may be present. So this is the spectrum of 3C273, which was redshifted by 0.158. That the lambda observed is equal to the emitted into 1 plus 0.158. And this is the composite spectrum. Now, when we talk about quasars, let me talk about the last kinds of objects to talk about. Let me summarize what we have done. Quasars, actually now, if I want to look at the host galaxy of a quasar, what do I do? For a long time, actually, historically, if you look at it, you need to be able to look at that fuzz or the galaxy to say what kind of a galaxy it is, right? So what happens is that you need observations of high resolution and also high dynamic. High resolution because if your resolution is poor, then it will smudge out and the whole object will come all over the galaxy. So you can't find out what kind of galaxy it is. So you need high resolution and you also need high dynamic range because you need to be able to see a faint object or faint emission from the galaxy compared to the very bright source. This became possible in large numbers, although there were hints about it earlier from ground-based observations. Became more, was demonstrated more clearly when we managed to do observations with the Hubble Space Telescope. Actually, even the HST got it wrong this time they published a bit. Saying that there is no galaxy. Then the data were reanalyzed and done that. Then they found that much better analysis of algorithms as well and much more careful. Reduction of the data. Every quasar around which you expect to see a galaxy had a galaxy. And you could classify them, although some of them were impact and some of them were less, but you could still classify many of them into the broad categories and spirals. But some were also messy and had signs of interaction. Now, when you look at the radio loud objects, the quasars that we talk about like 2C273, the radio loud ones generally tend to be quasars. They have jets, they have broad emission lines. Spirals will have broad emission lines, but the jets are not there, and they are quiet. So we see that the ones with spiral galaxies tend to be radio weak or radio quiet generally, whereas the ones with elliptical galaxies tend to be radio. Now, let me introduce you to a small idea concept. Suppose I had a volume of space and I had 100 quasars, 100 quasi-stellar objects, which means optically it looks star-like, it has prominent emission lines, and because it also has the color is bluish generally, because of the spectrum. Are all these powerful emitters of radio jets and radio emission? The answer is no. Okay? Only about 10% seem to be radio loud. Similarly, if I took a volume of space with, say, 1,000 elliptical galaxies, are all of them radio loud? Luminous radio sources? The answer is again no. For some reason, something triggers, we look at that aspect, jets are triggered with only seem to be about 10% of the elliptical galaxies. Whether it's cyclical activity or whether it is not, it's something we will discuss tomorrow. Right? So that is something which you should remember that although there is a continuity, but generally if you look at the most radioluminous objects, about 10% or so now are very luminous. Although you see that similarly for about quasars, about 10% are radio loud. Right? Now you mentioned about lasers. Laser actually is a term which is used to denote two kinds of objects. One is a category of objects near the Lacerti type objects, and the other is a category of quasars which are very strongly radiated. It's called optically violently radiated quasars. That means their magnitudes or luminosities can go up by huge factors even during the course of a night or two. Right. So these, because PL, quasar, SAR, so they combined the two to call them blazars. So quasars we've already met. I'll just introduce you to the term quasars, real-like objects. Now, again, this object too was discovered while trying to find radio counterparts of, optical counterparts of radio sources. We talked about how to find a quasar by looking at a star-like object and finding that they're very prominent emission lines. This particular object called Brazilian Radio Observatory 42.22.01 was also associated with a star-like object. In fact, that object was already catalogued as a variable star. And variable stars are named by combinations of letters like A, B, B, C, etc. Till they run out of combinations. Some combinations are omitted for historical reasons. Then they call it V, some number, and V. So this particular object was in a constellation research. And that's how it was variable star in research. Now, quasars, we found that it had prominent emission lines. Now, lo and behold, when it took a spectrum of the star-like object, it neither saw absorption lines nor emission lines. It had a flat cut. Okay? Flat cut, you know. So this is something which I would also like to remember. All right, let's see what it is. Here. So this is another real-like object. Okay? You can see there's hardly any bond. Look at the quasar over here and look at the real-like object over here. So now we know that there's amount of weak emission lines, but weak or no emission lines. Jets, when they are here and they radial now, and then generally these are just put this already over here. We'll like quasars plus optical line. So this is a summary of the going through. This is just a summary of what we have done so far. Okay. Now, just you know that you already answered it. That why should the lines be drawn? Because the lines are closer to the supermassive, right? So when we look at the canonical structure of the nucleus, what do we see? We see broad lines, we can see narrow lines, and we can see jets, and we can see a nucleus which may sometimes outshine the host galaxies. Now, medium loud and medium wide, and this that to you. And now, the picture, we'll come back to this later again. But you just revise because my day has already talked to you about this, right? A little bit. So what we see over here is that where geometry and orientation play a role, is that if you had a black hole over here, you had a black hole over here, this is just here now. Black hole over here, and if you had broad lines emitting close to the black hole, okay, and narrow lines are further out, then if by some means this is a donut-shaped structure which is drawn over here, which is referred to as a torus. So if you're used to Western food, it will be like a donut. If you're used to more Indian food, it's like a medulla, you know? So it surrounds this black hole in the center, and then there are jets going on in this direction. This is the black hole. There's an accretion disk over here, and this figure actually separates out two regions of here. One, the upper region is the radial loud objects we mentioned, and the lower region are the radial wide objects. Okay. Now, if you can hide this broadline region, then you can look at different kinds of objects in a similar way. Right? Now, we just talk about, because we talk about different aspects of this as we go along, but you can see that it's a scheme which can work. For example, this Super-2 galaxy, if I look at it from here, I will not get a view of the broad lines because the torus is going to hide it from my point of view, isn't it? Whereas if I had a line of sight which goes directly and sees these lines, then I should be able to see the broad lines as well, and then also see the narrow lines. So one possibility is that the Super-1s and Super-2s are the same objects, but they're appearing to be different because they are oriented in different directions respectively. Because as far as you're concerned, you're not in any special position in the universe. Objects will be randomly distributed in the sky. How they appear to us will depend upon how they are inclined towards our line of sight. Okay? Now, in science, as you know, I mean, you can see this and try to build a consistent picture, but you need to be able to test it. Right? How do you think you test it? Okay. You need to test. Is this theory correct? Right? So to test any theory, you need to make some prediction of what you expect. Right? And if your observations hold up to those predictions, that is, then you say, okay, it could be right. But in astronomy, what happens also is that nature is very diverse. Not every object may fall into your scheme, but at least a bulk of it fall into your scheme and say, okay, broadly it is okay. Some of you have read Philosophy of Science. You read Karl Popper, it's the science progresses by falsification. That means if you have to predict something, and if you test it out, and if it doesn't hold up, then the theory is wrong. Similar, Einstein's theory, for example, with so many predictions, everything is kind of right? So we hold on to it with our hearts. Okay, now how will we test it? So one way of testing it is as follows. So, for example, the accretion disk is hot, right? That's what we have also learned. It's generating a lot of high energy photons, right? Now, if there is no torus, suppose let's imagine there is no torus, then what is going to happen to these photons? They're going to go out in all directions, right? And these high energy photons, what will they do? They're going to ionize the gas in this vicinity, right? It will be weaker along further away from the source because the flux is going to go down. But when it is closer, you will see that they will ionize the gas in this vicinity, right? Without a torus, without an opening angle, the photons will go out in 4 by radians. There's nothing to stop them, right? The sun radiates in all directions. We happen to be in one location and trap some energy. But if there is a torus, if there is a whatever say over there, then it will be constrained. It won't be able to go out in 4 by directions. But it will still have a broad opening angle. It's not like a narrow jet, but it will have a broad opening. Along with the photons, will be able to escape. The other directions, it will heat up the torus, and the torus may emit in the infrared after getting heated up or at other parts of the spectrum, but the photons will not be able to escape in our directions. So I would expect to see cones of ionized material if I look for emission lines. Because what happens is when you ionize a gas, you strip electrons away, given the energy of the photon and species that are present, but they will also tend to recombine, right? So you will see emission lines from the gas, and if there is a ionization cone, then I would expect to be able to see these ionization cones. What do the observations tell us? You can see this. This is a Seyfert galaxy, C5728, and you can see these beautiful ionization cones. They're not always symmetric. They're often very asymmetric because one may be coming towards you, one may be going away from you. There'll be more absorption of the photons of the one which is going away from you, and it's in the medium. Also, the emission line emitting material may not be distributed evenly. Nothing in nature is absolutely symmetric. So, but you can see that there is evidence of it. At least indirect evidence that there is a difference. Right? And this is not the only case. There are many cases actually. I just picked up a couple of them to show that there is evidence for a torus. And sometimes you can image some of it in the spectrum. I'm not getting too much detail over here, but and jet is usually our problem into it. Okay. Now let's cover this over here. Now, the other experiment you can do is that, right? Now, what have we gone so far? We will take another 5 minutes. 5 minutes. What have we said? We have said that a Seyfert 2 nucleus and a Seyfert 1 nucleus are essentially similar objects, except that the broad lines are hidden from our line of sight. Okay? Hidden from our line of sight. Now, and we have constructed a geometric model where I'm hiding the broad line region. And at least one naive prediction of that scenario is something which seems to hold up to observations that if there is a manifold kind of structure, I expect to see ionization codes, I can see it. I want to go a bit further. Okay. This picture is correct. But I really want to know that are there broad emission lines sitting over there? There's a cone. Is it true that in a C42 galaxy, there really are broad emission lines? I'm not able to see it, but I want to find out by some means if it is there. Any thoughts on how you go about it? Suppose I'm sitting over here, sitting over there, and there's a huge wall set, or whatever, something separating us. How do you find out whether I'm there or not? Suppose I'm quiet. How do you find out? Or suppose there was a wall over here and you wanted to know if your friends across the aisle were there. You want to see them. How do you see them? Any thoughts? Sorry? Put a mirror. Very good. Exactly. Put a mirror. So then you have to ask yourself, are there mirrors in the sky which may be able to reflect it? Excellent. Put a mirror. So what can reflect? Suppose I have the nucleus over here, and I have electrons dust all over the place, right? Suppose I have a cloud of electrons or dust. You know that light can get reflected. So are there mirrors in the sky, effectively clouds of electron or dust, which may be able to reflect this light? And if it does, then what is the signature that it is reflecting? What does reflection do to light? Sorry? Sorry? Oh, the light rays are important. That's all right, but you don't know what the internal structure is. But one thing which light does when it gets reflected is that it fades, yeah, it will fade.
Changes its phase.
It can polarize the emission. So what I have to look for is, can I see polarized broad emission lines? And I also want to see them from the region. I don't see them from the region they're reflected. And for example, if I imagine that cloud is over here, right? Just for argument's sake, then if I see broad polarized emission lines from here, because there's no way I can generate those broad lines away from the nucleus. There's no supermassive black hole. Otherwise, I will see some of the signatures. So it's a very tricky experiment to do, but it has been done for a number of objects where you look for broad, off-nuclear, polarized broad-line emission. And this was done for the archetypal C42 galaxy at C1068. These are optical images. The radio has a jet. It's a emission line gas. At very high resolutions at radio, you see an axis orthogonal to this jet. People keep wondering whether that is a torus up from the machine possibly. Now, this was an experiment which is done by Relativistic and others. So this is the total intensity in the nuclear region. If you look at it in polarized light, you actually become broad lines, which are not from the nucleus, but are off nuclear, and it is polarized. So basically, what you're seeing is what she has said, that there's a mirror over there, but mirrors maybe in any direction, right? So you're not going to see it in every object. But at least if you see it in a fair number, you can say to a first order that this scenario is correct. So this is the way we sort of try to keep going. So this is just a cartoon of this person looking at type 2 and type 1, and seeing that type 1, you can see, if you see polarized emission, that you can see that there is a broad line region over there, which is actually hidden from our view, you take a direct view, you're not going to see that, but in some cases, it can reflect reflected towards your line of sight by minerals within coats in the vicinity of the nuclear tube, giving rise to off-nuclear, broad, polarized emission. So I think we finished at 3:30, although we started a bit late. So after we will, after community, but are there any questions that you want to ask? I don't know what we have covered today, or even going back to what Vaidya has covered, because we'll keep drawing upon what Vaidya has taught you. So if there are any doubts on what we have done today, after we'll go a bit more and we will look at trying to also understand asymmetry of jets, energy supply, generation, etc. But can take some questions now and then we'll
Regarding the regional features from the regional, what could be the example of the
for a rejuvenation. Rejuvenation. Okay. Rejuvenation. We will actually discuss that in greater detail tomorrow. But just to give you a short answer, that I will not get into black hole or spin right now. But basically, if say the black hole and spin are correct, and the conditions of the central region are okay to be generated. What you require is the creation of matter of an object. So the thing is that if your fuel runs out, then it's possible that your jets will not be generated. So you will need a fresh supply of energy or fuel to trigger the rate of jet. So you can look for evidences of the gases where, and a little bit of it will exist. Right? Basically, we will see today in the afternoon that the physical process which is likely to be responsible for the generation of this large. I don't think there's a big lectures on fission. So we'll do a little bit again to cover quite a bit. But basically, the creation of matter object. That is the way that you get the maximum or the most efficient way of extracting energy out. It is far more efficient than nuclear energy generation. So accretion is what is being. So accretion, if there is gas available for accretion, then you'll be able to generate these jets. If there is no gas, you will not. And the other factors which are also important, which we discussed about. Compared to planetary, yeah. Actually, the thing is that generally, that is what is observationally seen. The details of how these jets are produced is not realized. So, for example, in the case of planetary, what is believed is that there is a kind of this kind of structure because it's in a binary system. If it's a lone star, you just ship it out a spherical or quasi-spherical shell around it. That's what most of the planetary look like. But there are some significant planetary where you see there is complex structures. So it is believed that these jets, these binary systems actually form this kind of structure around them because they're rotating around each other. And this structure plays some role in the configuration of the plasma that is being ejected out. So the details are not observationally, generally, I think we say that we can go objects are better columnated than that's it. It's not very clear actually, because we have not made the direct measurements of it. Numerically, they are not calculation. So this with direct measurements of how much it is. There's some measurements from series.
I didn't understand how these mirrors work. How do they reflect?
How do they reflect? Okay. I mean, it is. Suppose I have this torus. I have the broad line. So all what is trying to say is that if you saw this object from here, this is the black hole. This is the black hole. And you have these broad lines. What you're saying is that from here, you're not getting a view of the broad line. You see this? Yeah. Now, if I have, if there was a, I mean, what do you need to reflect that? You basically need some dense cloud of gas or a cloud of electrons, which is dense enough that, for example, suppose I have a plasma or a cloud where I have electromagnetic radiation hitting. Some of it will get absorbed, some of it will get reflected. I mean, similar to our ionosphere. Depending on the frequency, it can completely absorb, some of it get reflected. For example, you can hear, whatever, radio silhouette or something because the ionosphere reflects the radio waves. Right? There would be, so similarly, depending on the properties of the cloud, with electrons or dust, some fraction of light will get. So as she pointed out, the density will decrease. So it's a very tricky experiment because you're not only diluting it by distance, but you're also diluting it by direction. So if you had similar kind of cloud over here and you're observing from here, it's considerable that in some cases you will have rays of light which are favorably disposed towards complete condition.
Is it right to say that these clouds will have high opacity?
They should have higher opacity to be able to reflect. I mean, some of it will get absorbed this way. So not all of it will get reflected.